Good afternoon. I thank you for the kind invitation from my research institute. Especially, thank you, Professor Wu Jianming. Today, I'm going to share a topic that I'm working on. It's called Revealing Wireless Channel Features, Reconstruction and Exploitation. I'm Tony. I'm from Singapore. So the outline of my talk today, first we'll talk about how the channel, as we proceed from 5G and beyond to 6G, how the channel becomes more informative. There are more features that we can extract from. And what is actually this environment defined channel model? How can we actually use this channel to exploit certain features that we need? And due to the time constraint, I'll particularly focus on the multi-domain channel reconstruction example. And I'll briefly talk about, besides reconstruction of channel, actually you can also do joint localization and channel reconstruction, for example, of extra large risk-assisted system. So let's proceed. The first part, the channel becomes more informative in 5G and 6G. So let's talk about 5G. If you look at 5G, there's a three application scenario that we know. There's EMBB, enhanced mobile broadband. There's ultra reliable and low latency communications. There's massive machine type communications. So each of these services actually requires different specifications. For example, much higher data, much low latency, massive connectivity, and that actually motivates why 5G particularly want to go to essentially a higher band. That means one of the few key enablers in 5G physical layer. First is wave, millimeter wave. Why? Because millimeter wave frequency, you have a huge chunk of unused frequency resource. As we know from a sharing capacity, with a larger bandwidth, where bandwidth is essentially in front of a log term, essentially we can increase the capacity much faster. So having that's one of the motivation why we want to go to a wave. Another key enablers in the 5G physical layer is this massive multiple input, multiple output. So the concept is essentially the same. When we look at the sharing capacity, essentially you want to increase the multiplexing game. So besides spectrum, another way of increasing is spatial dimension. So by deploying massive antennas at the base station, the spatial domain multiplexing gain, which is the M factor, can be substantially improved. That is, you can increase the number of orthogonal data streams, and that will increase your throughput, which as we see here. So you have essentially a sum of parallel channels. That's one very easy way of increasing the capacity. So as we move from 5G to 6G, and we look at the 6G vision, there's a few technology we see. It's a continuation of what we see in the 5G, where you want to exploit the spatial domain and the frequency domain. One is more spectrum. You want to have more bits, and you see that in 6G, there's a push to go beyond the millimeter wave spectrum up to even 100 gigahertz, terahertz. And at the same time, you look at the antenna elements. From massive antenna elements, now we go to large intelligence surface, where the whole concept is increasing the spatial domain. So let focus particularly the key enablers as in 6G physical layer. As I mentioned, now from millimeter wave, you're moving up to terahertz, where you can go all the way to 3 terahertz. So there's large of unused spectrum. Of course, standardization or WRC will actually decide what are the spectrum that will be standardized across all the different parts of the world, where that will be the terahertz bandwidth people use. But what is actually distinctive from 5G is that now as we move up the higher band, now besides communications, you essentially can use this millimeter wave or terahertz band more than just communications. It will be a sensing capability, imaging capability, which means that now the channel becomes more informative, and there's a structure that allows you to actually exploit this additional capability, which is actually the focus of this talk today. At the same time, as I mentioned, now we are going into enhanced massive MIMO, right? Now, because the fact that you're going up to a higher band, actually the antenna elements, you actually can make it smaller. You can deploy on the wall of the building, you can deploy on a room. So for example, extra large antenna array or reconfigure intelligent surfaces, the near passive one. So essentially that's in the form of massive antenna, enhanced massive antenna, which means that you can actually you actually can exploit the spatial domain in a very precise way, which we'll actually elaborate more in the next few slides. So to be more precise, now we say the channel becomes more informative, but in what sense? For example, in a delay domain. Just a simple example, we look at high resolution delay power spectrum can obtain from a wide bandwidth. So let's look at a narrow band system. So you have the channel impulse response, then your transmitted signal. If you go, and that's your receive signal. So that's for a narrow band system. So a narrow band system, that's you will not have a very fine resolution, but for wide band systems, right? For wide band systems, because the bandwidth is large, though, from the time domain, actually you look at the pulse is actually very short pulses. Then you watch actually distinctive, you see that's the resolution of the pulse. So you get more fine details of the channel in terms of delay domain. Now you can see the actual the different pulses due to the delay, due to the channel impulse response. But for narrowband, you see one whole chunk. That's you see in the delay domain, you see more information. What about spatial domain? Now, as we increase to a multiple antenna element from a small numbers to a massive number, now you have very sharp angles. So very fine spatial direction. So you actually can pinpoint where the location of the user is. So that's the channel becomes more informative in the spatial domain. Now let's look at in terms of a model, but to that we build up some of this mathematical understanding of this channel model. First is large scale fading, right? From radio spectrum, radio channel, we have large scale fading. Large scale fading models what? Models the path loss and the shadowing. So path loss is essentially determined by the distance between the transmitter and receiver. So this is a very simple path loss model. Shadowing happens to have a large construction such as a hill or large number, and that defines the random variable here, which is depends on the model. One common use is a log shadowing model. Next is the small scale fading. Small scale fading actually models the multi-path fading. So essentially, you can look at from a transmitter to a receiver. Receiver can be a handphone because all the different reflection, angle, reflection. So the signal that you receive at the handphone suffers from a different reflection scattering caused by the different surfaces, right? So you have a line of sight, then you have all this reflection, and this is actually a cumulative effect. So if you look at this cumulative effect of this fading channel, so this is a very common plot. This is 101 wireless channel, where you will see this plot of the channel gain with respect to distance. You see this linear line, linear lines that actually declines with respect to distance. This is due to path loss, right? With path loss, then on top of path loss, now we have large scale fading, we have shadowing effect. So you will actually see a smooth curve going following this, but on top of the smooth curve, you see a lot of fluctuations going up and down. And this is actually due to the small scale fading because of the construction and destructive interference of the multipath fading. So that's actually the total effect, actually what you see from the channel. So now we go precisely down to the multi-path components, because these were actually able to extract useful information that we can actually use for different applications. I will elaborate. To do that, let's look at a few simple models. Now, if you have a transmitter, you have a receiver, you have a single line of sight. So you can imagine this is from a space point of view. I'll have one line of sight. Then if I have a reflection from a smooth surface, I will have actually a single very peculiar path, right, from the transmitter to receiver, so that essentially captures the surfaces. But then once I have a rough surfaces, you will have one single specular path, but then multiple diffuse paths from the environment. So actually, from that information, we can actually have some sense of what type of surfaces or the reflection surface are. So the specular and diffuse path are these non-line of sight. These are called the non-line of sight paths. So this is my model. Now, precisely, we go into the parameters of each path. First, you have a complex gain. So complex gain G essentially indicates the path loss and the phase shift that the signal will experience when traveling along a certain path, right, from a transmitter and receiver. This complex gain is proportional to actually the distance, inversely proportional to the distance. And the complex gain is actually determined by location and rotations of the transmitter, receiver, and surface. So this is one case where you have a line of sight, one case that you have a smooth surface, then you have actually one reflection. So this is a reflection. And I want to point out from terminology, this is my transmitter, then you actually can map it to something called a virtual anchor. Image of the receiver of the user, in this case, transmitter with respect to the surface. So this is my notation PVA, which is a virtual anchor. So the next parameter is this angle theta. Angle theta from 0 to 2 pi describes the spatial direction that the signal will travel through, right? It comes from which direction? So base station. So this is my angle of my line of sight. Angle likewise is determined by location, where we are, located on transmitter and receiver. So now you have a base station, you have the user, this is my virtual anchor, you have a single reflection. So this is my non-line of sight angle. Another parameter, as we mentioned, multipath, so you essentially have delay. Delay is what? Delay tau indicates how long the distance the signal will travel, right? To reach the receiver. So this is a notation, while this is my delay for my line of sight, right? And because we are using real frequency, so this is my speed of light. And delay tau is actually determined also similarly by location and rotation of the transmitter and receiver. So this is my receiver, this is my transmitter, and this is my delay for non-line of sight, right? So if I put all these parameters into my model itself, my model channel is modeled by the sum of multipath components, as you see in some slides ago. At the receiver is actually a sum of all the constructive and destructive number of multipaths. In this model, now at this frequency and this antenna, M, L is the number of paths coming in, the line of sight, non-line of sight, and have a complex gain with respect to the L path. I have a phase spatial angle that coming in from respect to the L path. Then I have a delay tau L with respect to the L path. So a path is described by a complex gain, a spatial angle, and the delay. And this parameter, I explicit channel state information. So you see that this is sufficiently tell me about my channel. So my channel gives information on the environment as we see. From there, I have delay, I have angle that coming in, I have gain. The multipath channels gives really information of the environment, including location of target surface. Can we enabling sensing with CSI? So as I mentioned just now, one of the applications as we go up to higher band with 6G is that you want to have a sensing capability. So it means sensing capability, I need to capture direction, distance, velocity, position, or image of the target. So you want to get that from the informative channel. So sensing also can involve obtaining a map of wireless propagation model, identifying the surface in the environment. So we'll look at some of the examples. So let's say user localization. I want to know where the user is. So given the CSI, I know the delay of tau, L, theta L, and the information of my environment. How do I actually obtain the location of user? For simplicity, we look at the case one. Let's say I have a single path, a single line of sight, right? Base station to the user. Since I know my delay, since I know my angle, then you know that the delay tau L decides the distance, the spatial angle, theta line of sight decides the direction. So my location of the P user can be easily obtained, right? I can find the location of user based on my location of PBS. I know my delay, I know my speed, I know my angle coming in. Then with that, I actually can pinpoint where's my location of user, right? For line of sight, actually very simple. What happens if you have reflection? Likewise, singly, let's look at a simple case. You have a single no line of sight. This is my this is my base station or transmitter. This is my receiver. This is my virtual anchor. Likewise, my channel model can be described as follows. An obstacle exists between the base station and signal. That's why I don't have a line of sight. So I have a single no line of sight path. A smooth surface, since I know the environment, the smooth surface reflects the signal. So I have a reflection. This is my virtual anchor. And I can actually first find out where's my virtual anchor, because that is my line of sight. So we can use what we have seen in case one. I can find where the position is. Since I know where's my position of the virtual anchor, from there I can subsequently infer where's my user, because this is a direct image of my user. So that's a very simple case verification. Now, what happens if you have a lot of paths, right? As we see the multi-path channel model, sum of L, if I know estimate L, I know the exactly number of paths. Likewise, we still can find the user. And from the CSI of the virtual anchor, right? The virtual anchor will coincide with a particular surface, will coincide with the surface of VA for over all the path here, right? With all the reflection, they'll be coming over here. And essentially what we actually can do is to find the position of user. We use the argmax, right? Search over all of them, and find the position that gives you the one that have all the CSI virtual anchor coincide, right? So this gives you the approximately best estimates of the location of the user. So this is one example of housing use the channel to actually infer the location. Well, environment mapping. So given the CSI, let's say I know the delay, I know the angle, and I know the user location. Is there a way to obtain the map of the propagation environment? So we transform the CSI, for example, to surface information. I cluster the paths into multiple groups based on my delay, based on my delay spread, and one group. I can actually infer whether is it a line of sight, is it a smooth surface, or is it a rough surface. So the whole idea is to transform the CSI to surface information. So one path corresponds to a scattering point on the surface. I find the location of PL, and based on tau L, TL, and the position of base station and user, I stitch the points into a group together as a surface. Of course, the limitation of this approach that I only can find whether there's a single point on the smooth surface or part of a rough surface. So if you have more information, then I can infer better about the environment mapping. So this gives you some example, very simple example how we actually can use the information from the channel. Let's look at actual applications, right? So this is a recent paper that we have, and the motivation is that the whole idea of wireless communications, whether it's 5G and beyond, is to exploit the resources in the multiple domains. Right, multiple domains to guarantee high quality of mobile communication services. We know time domain, you can use time domain, you can use frequency domain, you can use polarization, antenna polarization, as we also mentioned, the spatial domain or user domain. Now, if we look at that, then an example of FDD massive MIMO downlink, the challenges is to get the channel state information, right? You need to acquire that. And what is in practice, you send orthogonal downlink pilots, and if you have a huge number of massive base station antenna, then you need to get a feedback to get the actual matrix of the channel, which costs a huge amount of resources. If you have a time varying channel, you need to track the channel. If to track the channel, you need to track it quick and track it accurately, and that requires a huge amount of training overhead over a short period of coherence time, where the period of time where the channel remains constant. And if I want to acquire the CSI of huge number of devices, as we say, one application is massive IoT or mesh devices. So for each user, I need to acquire the CSI. So for fully orthogonal independent training among all these users will be very impractical. So what is this go over? Is there a way that we can actually reconstruct the channel for this multi-domain problem with reduced overhead and low computational complexity? So let's look at a very simple model. So I have a system model of user. I have K close by users. Users are close together. There's a polarization domain. So this is my angle, and a spatial domain. The base station use a uniform linear array with M the antennas. And time domain, I consider a long period of T continuous strain, sufficient time so that I can actually acquire my perform my channel reconstruction. In this system, I assume there's a frequency domain is the FDD OFDM with N subcarrier. So conventional way of trying to measure this FDD massive antenna type of applications will require a lot of pilot. So this multi-domain channel model is denoted as follows. So I want to reconstruct this. I want to reconstruct this And the reconstruction of this multi-channel model, as we see the few examples in the first few slides, a simple scenario, I need to involve the estimation of parameters associated with the path of each domain. Now, because I have a few domains, I have time domain, I have frequency domain, I have polarization, I have spatial domain, I have K user. So my number of paths will be a function of KFT. I have a complex gain of path L, the angle of path L, and the delay of path L. So this is essentially, you can see it's just a generalization of what we have seen in a simple multipath model. So for uplink channel of user K in polarization P and frame T, so I can actually write my uplink channel model as follow. So this is my steering vector of the uniform linear array. So steering vector with respect to the angle. And this is my phase shift vector across the OFDM subcarriers, and this is my channel gain. Right, in practice, we know that there's a correlation, the environment, because it's shared by adjacent frame, frequencies, adjacent polarization, antenna, and users. So correlation of channel exists in each domain, whether it's time, frequency, polarization, antenna, or user. So the whole idea of this, can we actually exploit this? So we look at this in a bit more details, correlation of channel, time domain. So let's say the duration of frame is only 10 milliseconds in the current mobile system. The variance of channel is, you actually cannot differentiate within this short period. So there's a high correlation in terms of time. Frequency domain, signals in uplink and downlink propagate in a common environment. So the environment is the same. My base station is there, my user is there. So the channel, they travel along the same propagation path, although the uplink and downlink spectrums are different. But then as long as they're not separate two paths, we see a correlation over there. Polarization domain is the same because although the antennas are in different polarization directions, but they are co-located. Spatial domain, all the antennas in arrays see the same scatterers, right? It's because of the same environment. User domain, close by user gather in small region, let's say a theater or a stadium. So there's a correlation among the users. So how do we actually try to exploit this correlation? So the whole notion is this maximum variance based parameter model. So path parameters let's say in a resource subset A of a domain, let's say it's assumed to have certain relationship with that of another resource B, right? For example, delay tau B across path L, tau A across path L. There's a linear relationship with respect to the delay in two domain, the angle domain, and essentially I assume that tau is actually uniformly distributed across -half and half. So regarding this resource subset S as a reference, we have a reference set, then actually I can extrapolate tau B theta from this reference set with reduced cost, because I just need to know tau A and theta A. I actually can extrapolate to get tau B. And so this is our proposed idea of a low complexity, low overhead channel exploration that make use of correlation of a channel across all the different domains. So how do we going to do this? So it involves two phases. First is the reference channel, right? I need to find the reference channel. So for reference channel, I need to reconstruct. So I need to learn that channel from the environment. We see that the channel has sufficient information for us to learn. Then the phase two, I'll do a channel extrapolation with a reduced amount of pilots. So this is a diagram we can see. Okay, so my reference channel, let's say user 0, frame 0, polarization 0, uplink. So this is my reference guide. So if I can actually learn from environment and know this reference parameter, then actually I can infer, let's say from a frequency and space domain, I can find the downlink, I can find the polarization domain of the other guy, time domain from frame 0, I can find frame 1, or from user 0, I can infer other user, let's say user 1 to user K-1, because they are co-located very closely together. So there's many domains that you actually can extrapolate from the reference. So how do you actually reconstruct the reference channel? So we look at sparsity. So as we have massive antenna and go higher frequency, there's a channel sparsity in both angular and delay domain. So my angular and delay domain, I can write this as a matrix. Essentially, you can see from a plot diagram in terms of the delay and both angular and delay domain, we can see that these are points in this two-dimensional image. So you see that it's actually a very sparse type of matrix. So there's a very sparsity in the angular and delay domain. So how do you actually can reconstruct this? So there's two ways of doing it. One is very popular in this compressing sensing or sparse signal processing technique. One is to use NOMP, so it's Newtonized orthogonal metric pursuit. So the whole idea is iteratively extract the path components from residue in a greedy manner. So in each iteration, the spatial angle and the delay of a path is first of all costly estimated from grid. Then you do refinement. So this is one way of doing it. Another way is essentially, as I mentioned, is you can view this as an image, right? It's a sparse image. So you can use a computer vision idea. So YOLO neural network, you can actually find objects in the network by using this image. So you actually regard the angular delay domain as an image, and the spots can be actually estimated using a neural network. I'll not go into the details of the method. So assuming that now I have finished my channel reconstruction of my reference channel, then I can extrapolate. So this, we can look at this from a delay and angular domain. So if I have a certain point, I actually can extrapolate to find the parameters from the other point, right? But then I want to use a reduced pilot or reduced codebook. How do I do it? So I use a low overhead extrapolation. Of course, I can use a full pattern. So there's many ways of using these pilots to help you. So we'll look at whether it's uniform dense pilot pattern, cost sparse pattern, or randomized sparse pattern. And we find that the randomized sparse pilot pattern provides the most accurate extrapolation, because the reason why is because from the reference channel, the user can be anywhere, right? So you look at some numerical results. The base station, number antenna 128, number of OFDM carrier 128, close by user 6, I have a continuous frame of 5. The whole goal is to reduce complexity, so reduce pilot reduction of a quarter 1/8, and the performance metric is normalized mean square error. So first of all, we look at the performance extrapolation in a single domain, right? In a single domain, we compare across the different pilot scheme. And for example, the full pattern will give you the lowest. Of course, the full pattern requires too much pilot. But then if I have a pilot reduction of a quarter, we see that essentially the sparse random gives you the best performance. Then subsequently you have the comb, and then this is the dense uniform, right? This is for the pilot reduction of a quarter. This is pilot reduction of 1/8. We still see that, of course, there's a loss compared to the full pattern. But to take in mind that we have a pilot reduction of 1/8 or 1/4. So in summary, we can see that the reference channel reconstruction, you actually can first of all get the sparsity, channel sparsity, angular and delay domain. Then you can do a construction using NOMP or YOLO from neural network. Then you do an extrapolation using all this codebook method, and you see that actually the performance is acceptable. Because you only have reference channel from one, then you actually can extrapolate. So due to time constraint, I will only briefly talk about another application. So this will be doing localization and joint reconstruction. So we look at the scenario of, as I mentioned in the 6G, one of the key technologies with this reflective intelligence surface. So you can imagine this is another form of enhanced passive antenna, but it's a low cost, near passive surfaces. So the whole idea is to control your direction of the electromagnetic wave and produce a preferable radio propagation environment. Then this is particularly useful for example, millimeter wave and terrorist applications to improve the coverage. So the risk can be deployed in systems to provide this additional link to guarantee a high quality of services, and it's low cost and it can be made large or spread across different surfaces or on the wall of a building. So the goal here is to actually localize and channel reconstruction, because likewise, as a large surfaces, you need to estimate the channel, right? So you actually need to do the reconstruction, channel reconstruction of the wrist link. So it's passive. So wrist does not have very active sensors, so does not have very sophisticated signal processing capability to estimate, for example, the channel from the base station to the wrist to the user, right? Because it's a surface, so actually you need to actually estimate this channel. And most of the work opt to estimate the cascaded form. But we know in practice, it is not just a cascaded. The properties could be very different because it's a near field, then this could be a far field. So if you have a very huge wrist surfaces, you have many units. For each unit you want to measure channel, a huge number of overhead. Right. Here I will not elaborate into the techniques we use. If you're interested, you can follow the paper, but I'll just give you some of the results we have and show you that even with this scenario, that you actually can localize and also to do the channel reconstruction. So our scenario, you're looking at the number of base stations 32, the number of wrist units is 256, number of users is 4. These 4 users is really close to wrist surfaces. The number of pilots, we want to reduce the number of pilots, the number of multipath. You are looking at a wave, so it's 28 gigahertz. We have a precise location, let's say location of the base station, and this is my wrist surface region. And this is my transmit power and noise power. The whole idea is that I need to find the user. So in the paper, you will see that there's a 3-step, right? Why there's a 3-step? Because it involves 2 channels, one from base station to wrist, then wrist to the user. To precisely find this, I have to estimate this, and the localization accuracy can be enhanced. So you have more wrist units, I can improve. So you can see in this result, I have a real user. This is a proposed location. And this is my reference model from another paper that you see actually is very accurate. And as I increase the number of elements, because my spatial angle becomes more fine, I actually can localize much better. So there's another use of this wrist that besides improving the services, I also can localize my user. And the performance of my channel reconstruction here, because I also do both channel reconstruction and localization at the same time. And we have proposed some method, and our method is called Reconstruct, taking into the precise type of the channel properties, because a lot of papers is a cascade. It's actually more than a cascade. By taking into the actual channel effects of near field and far field, actually you can propose a much better scheme. So the whole idea here, there's two parts. Because first of all, I have a channel reconstruction, I have a user localization. The VR identification is method actually related to my channel construction. And if you're interested, please refer to the paper. I think you can available in this IEEE Explorer. We can actually accurate all this region, find the user location, and reconstruct the separate channels using the proposed scheme. With this, I end my talk, and I thank you for listening. Thank you.